Hey everybody, Vade here, and today we're going to be deriving the unit circle. Oh my god, this is going to be awesome. So, just FYI, I haven't formally made a video on special right triangles, but I am going to do that in detail in a future video. But right now, for this video, it is assumed that you know your special right triangles. Now, of course, if you're watching this in the future and I already have a video on going over or proving the special right triangles, please watch that before this. But for now, just assume that you know your special right triangles. Now, one thing that I'm going to do in this video specifically is I'm going to do things in terms of radians, because in respect to trigonometry, we are going to just be using radians today. Now, if I have time at the end, I will put the degree measurements, but hopefully you know how to convert between degrees and radians. For example, if you have radians, you just multiply that by 180 degrees over pi radian. Or if you have degrees, you will just do pi radian over 180 degrees. So those are the conversions. I will again go into that in more detail in a future video. So just the quick facts here about the unit circle while I draw this here. Okay, we're already done drawing this, but let me give you some quick facts here. Firstly, the radius of the unit circle is always 1. Okay, this is important to know because when we use our special right triangles here, our hypotenuse is going to be always be the radius of our unit circle. Okay, that's going to be very important. Secondly, the unit circle, just more of a real life kind of in practice fact about it. It's commonly just memorized by students, and often algebra 2, trigonometry, pre-calculus, whatever teachers who introduce the unit circle often just give it to them and tell them to memorize it. Or at least just sort of allude that, oh, this comes from special right triangles that they themselves don't explain at all. So that's why I want to go into it in detail. Again, I will make a video even going into this in more detail, especially with the special right triangles. But for now, I just want to get a video out there going in this in as much detail as possible, because I want to make a separate video on special right triangles just because of how important they are. So anyway, let's start off with our first angle on the unit circle. I'm going to stick with the first quadrant here because, again, unit circle, you will have to, of course, remember it at the top of your head. But again, that peace of mind that I keep talking about, you know where this comes from, right? If you are studying for a test or whatever, and you have to know the unit circle, having that peace of mind that, oh, I know where this comes from, is always really good, because it makes the math less frustrating and, of course, potentially interesting for you. So let's start off with our first angle, which is going to be pi over 6 radian. So pi over 6 radian, equivalent to 30 degrees. And the reason why I'm mentioning that is because of 30, 60, 90 triangle. I'm just going to be writing it as pi by 6, pi by 3, and pi by 2 triangle. So this is, of course, pi by 6. This is, of course, pi by 3, and this is our pi by 2. So, of course, again, I haven't drawn the circle yet, because I'm going to do that at the end. But our hypotenuse is the radius of this soon-to-be circle. So I'm going to write that as 1, because I just told you guys that the radius of the unit circle is always 1. That's just by definition, okay? Hence the name unit circle, right? Like if you've heard of a unit cube, it's just a cube with all the edges being 1. So if this is 1, knowing knowledge of special right triangles, again, assumed for this video, if this is kind of like our 2x scenario, so if adjacent to the pi by 6, that's just going to be x, which, again, if this is 2x, it'll be 1/2, and then root 3. Okay, and in the common way representation of the unit circle, this is just written as root 3 over 2, but of course equivalent statement if you say 1/2 square root of 3. And now adjacent to the pi by 3 angle here is going to be 1/2, because that's just like our x, like 2x is 1, x is 1/2. Okay, again, if you don't know what I'm talking about, it's assumed that you know special right triangles, but of course if you don't don't watch this video just yet, I will make a video on this in the future, promise. So now you're probably like, why did I do all this? Well, I want to get a coordinate pair. Okay, and you're probably like, well, why do I need a coordinate pair? Well, I'm going to talk about it. So x comma y is what I want to get here. So remember, x by definition is the horizontal movement, right? Hence the x-axis, and y is the vertical movement, hence the y-axis. So we think about our x comma y here. I go root 3 over to the right and 1/2 up. So this is going to be, right, x coordinate is square root of 3 over 2 horizontal, and y coordinate vertical is 1/2. So now, why did I use a coordinate pair? Well, again, this is also, if you've had to memorize the unit circle, you've probably seen coordinate pairs, and they often have no context, but I'm about to tell you the context behind it. Since this is the angle pi by 6 here, and we're thinking only about these angles here, central angles, if you think about pi over 6, we want to do sine of pi over 6, so that's, by definition, sine is opposite over hypotenuse. Sine of pi over 6 is 1/2 over 1, which is 1/2. Y coordinate. Cosine of pi over 6. Cosine by definition is adjacent over hypotenuse. Watch my right triangle trigonometry if you're confused. Video if you're confused. That's just adjacent square root of 3 over 2 over hypotenuse, which is 1. And square root of 3 over 2 over 1 is square root of 3 over 2. So our x coordinate is cosine, right? So what I want to kind of say here is that cosine and sine, right? Cosine comma sine is the same as x comma y in the unit circle. And this pattern is true for all of our angles. Super cool. So please have that in your head, that our x coordinate on the unit circle is cosine and our y coordinate is sine. Because, and of course, just look at this triangle if you're confused. So what I'm going to do here is I'm going to erase this. I'm going to keep our angle here. I'm going to erase the triangle. But I'm going to drag this to the side because we're going to be using this later. Again, this is my first time making this video. I haven't even rehearsed this video, so I'm just going to go with the flow here. So now I'm going to draw another triangle. Another triangle. And this time with pi over 4. You're probably like, why pi over 4? Well, pi over 4 is the same as 45 degrees. And hopefully you've heard of the 90, 45, 45 triangle. Or in this case, I'm going to say pi by 4, pi by 4, pi by 2 triangle. Special right triangle. So radius is 1. So our x root 2 is 1. So x is 1 over root 2. Since this is an isosceles right triangle here, these two sides are congruent, so it'll just be 1 over root 2. 1 over root 2 and 1 over root 2. But, of course, we like to rationalize, of course, in the unit circle context. That's how you usually see it. You see everything rationalized in a unit circle. But again, 1 over root 2 is the same as root 2 over 2. Okay? You can rationalize to check. But that is a true statement. And the reason why is just because this is the normal convention people like the neatest answers possible. But if you write 1 over root 2, that's completely acceptable. So our coordinate pair here is root 2 over 2, root 2 over 2. So this is, of course, still our cosine and our sine. And another way of thinking about why this is constant is because, of course, hypotenuse is always 1. Opposite over hypotenuse, opposite over hypotenuse. These horizontal and vertical movements here, they're just divided by 1 for the, for both cosine and sine, right? Because both of them are over hypotenuse by definition in the denominator. So I'm going to erase this here. We're almost done. Just one more angle in the first quadrant here. Well, actually, I'm going to do 2 more angles that are right on the both the y-axis and x-axis here, because those are important too. So let's do our final angle officially in the first quadrant. So this is going to be, and hopefully take a guess here. And again, these triangles, keep in mind, FYI, these triangles are not drawn to scale at all. Okay, I'm just trying to illustrate that they are right triangles. Okay, not drawn to scale at all. Okay. So this is going to be our pi over 3 angle. Actually, oops, I need to get this guy here, because I need it for our next steps. Okay, get this guy out of here. Thank you. So now we have angle pi over 3, which is equivalent to 60 degrees. So hopefully you see here that once again we can use our 30, 60, 90 triangle, or our pi by 3, pi by 6, or 60 degrees, 30 degrees, whatever. Pi by 6, pi by 3, pi by 2 triangle. So this will of course in this case be pi by 3 central angle, and then this will be pi by 6, and this is pi by 2. Again, radius is 1, so hypotenuse is 1. So then this will be, of course, using special right triangle terminology, this will be 1/2, and then this will then be square root of 3 over 2. Again, I'm taking it off of this guy right here, which we just did. Hopefully see that it's just in reverse. So then this coordinate pair will be 1/2, comma, square root of 3 over 2. Perfect. Okay. Let's get this guy out here. My first time making this video, so I want to try to get it, all in one take, if possible. Oh my god. Sorry about this, guys. I just really don't want to rewrite this, just for time's sake. Okay. This will go right here. So now I'm just going to deal with these guys right, and I'm going to actually use a different color here. I'm going to use blue, just to illustrate these cosine and sine values. So this angle right here, right, because we start at this is, again, just how we use circles and angles in trigonometry here, especially on a Cartesian plane thing here. Cartesian plane. We start at the initial side, which is the positive side of the x-axis, and then we go clockwise, and then of course this guy right here, whatever this guy is our terminal side, what I just drew here. So initial side, positive side of the x-axis, terminal side could be anything from there, but going in the clockwise or right direction. So with this in mind here, this is actually going to be both 360 degrees, because hopefully you've learned enough trigonometry to know that there's such things called coterminal angles, and hopefully this helps. If we think about a revolution, which is going 360 degrees, again, I'm using degrees here just for it to be a little, because people are not used to radians as much as they're used to degrees. That's just a fact. We all grew up in elementary school talking about degrees, in middle school, whatever. So we have some angle here, like, I don't know, 35 degrees. If we take one revolution, again, I'm going to try to draw a circle here. That was a bad circle. Assume this is 360 degrees from the 35 degrees. 35 degrees is the same as 35 degrees plus 360 degrees. This is just a fact, because if you take one revolution, you will end up at that same place. Okay, so that's why if we start at 0 degrees here, this is 0. Again, I just explained why, because initial terminal. This is 0. So if this is 0 radian, or 2 pi radian, the reason why is because of coterminal angles. So radius here is 1, right? Radius here is 1. The length, think about a circle. Think about a circle like this. Again, that circle at the end is going to be terrible. This radius is 1. So thinking about our vertical and horizontal movement, because we just identified that pattern with sine and cosine. Vertical and horizontal. Horizontal is 1. Vertical is 0. We moved 1 unit to the right, but we moved 0 units up. Same thing here. This is a radius 1. Think about like a circle. That's a really bad sketch. Radius is 1. So this right here, we didn't move anywhere horizontally, but we moved 1 unit up vertically. For the sake of time, I'm going to just get these other ones in place. So if this is a unit of 1, but we moved, again, since we are on the Cartesian plane, we're thinking about location. Okay, so this is right here going to be 0, -1, just because this is a coordinate system, okay? But the length, of course, can never be negative. This coordinate pair just resembles location, okay? So that's why we need it, and because the cosine and sine values depend on the location. And then this right here would, of course, location-wise, be -1, 0. So again, that was just for time's sake. I just got all those out of the way. But yeah, I don't know how I'm going to get this blue out. I can just draw over it. I don't know. So now I'm going to go one by one here and talk about, and I'm going to go back to for example, our pi by 6 angle here. Start off with this guy right here. Let's go to the second quadrant here. So I want to first exploit symmetry, okay? Because I'm not going to do the special right triangle thing necessarily with it. Okay, I wanna exploit some symmetry here. These next angles are going to be these lengths right here. 1, if this is 1, then this exactly symmetric angle here, right? This angle right here, which is, and we're going to talk about the relationship between the pi by 6 and this mystery angle. the radius is also one. Like, of course, it doesn't look symmetric by my picture, but assume this is symmetric with respect to the y-axis. I know it looks not asymmetric, but it is. Assume it's symmetric. Think about our coordinate system. Think about even functions. You guys hopefully have learned even functions. The whole f of x equals f of negative x thing. This coordinate pair right here will just be, since we are on the negative side of the x-axis, this will just be negative square root of 3 over 2, comma 1/2. That is super cool. This is very intuitive, because if you know the first quadrant, you will know all the other coordinate pairs in the unit circle. That's why I spent so much detail, so much time going over the first quadrant, because that's where like special right triangles are really handy. The rest, you can use special right triangles, but we're just going to exploit some symmetry and just some pretty visual relationships we can see. So this is, of course, true with all the other ones. Like, for example, again, I'm going to talk about the angles in just a second. This will just be, of course, 1. We saw that this was like the pi by 4 on in the first quadrant. So this will just be, again, x is negative, but y will be the same because we're in the positive y-axis. Negative root 2 over 2, comma root 2 over 2. Same thing true here. Okay, I can right here. Mystery angle. It'll just be negative 1/2, comma root 3 over 2. So now let's talk about the mystery angles. How do we find, I'm going to actually write this here, because why not? Actually, I don't, maybe I'll need these. I'm not, yeah, I probably will for the third and fourth. This will be, again, negative square root of 3 over 2, comma 1/2. If we think about, remember, initial side to terminal side, I want to go from here to here. Okay, sorry, this is not a perfect semicircle. I want to go from here to here, positive side of the x-axis to negative side of the x-axis. This should be pi radian, or 180 degrees, half of 360. Hopefully that should make sense. So if I want to get this angle here, and of course we have to use the logic of initial to terminal. So if I want to get specifically this angle right here, I wish I could draw semicircles properly. You get what I mean? I want to get this chunk right here. In order to do that, I'd need to do, again, hopefully this should make sense here. I need to take this angle. Let me find a better way to explain this here. I need to do 180 degrees, or pi radian, minus that symmetric angle. So if I do 180 degrees minus this pi over 6 here, or if I do pi minus pi over 6, that'll be our angle here, because this is, we're going from here to here, which is pi, but then minus this, and these are symmetric. If we do that minus this, let's cross this out, pretend that's not there, we'll get this from initial to terminal, which is this angle that's symmetric, right? Because if we don't follow the logic of initial to terminal, just these angles itself, if we're not talking about initial to terminal, are the same. And that's because, symmetric, we can use symmetry, right? These coordinate pairs, it's just same y value, just this flip-flop went to the negative side of the x-axis. So, really, for all these angles, you just need to do pi minus its corresponding angle to the first quadrant. So this is pi minus pi over 6. This is pi minus pi over 4. And this is pi minus pi over 3. Hopefully this makes sense after my explanation. My explanation was pretty messy, but hopefully you got it. And again, I just set it in degrees because people are used to degrees. 180 degrees, half of a revolution, then minus that like symmetric angle. I don't know if that's like correct usage of terms, but like the angle corresponding minus that will give us that entire angle. And so pi minus that corresponding angle will give us that. And then if we actually simplify this, right, using common denominator, this should be 2 pi thirds. This should be, 3 pi fourths. And then this should be 5 pi sixths. Okay? Awesome. Great. Really good. Amazing. Let's exploit some symmetry again. I'm actually thinking I didn't need these exact same copies. Yeah, I just need this guy because if I prove my point with one of these, it'll work for all of these. So I'm going to erase this. And again, unfortunately, you get to see the entire like unit circle as one piece. But I am going to go over every single part of it. Just because it's an iPad, I can't really be super... I could have just done like a blank unit circle kind of thing, but I want to do it from scratch. So, yeah. Let's exploit some symmetry again. Okay, but this time some x-axis symmetry. So, corresponding here with it's pretty similar logic again to the y-axis symmetry here. So if I look at this angle here, we didn't move horizontally anywhere. So this is going to still be square, and we'll talk about angles in a second, square root of 3 over 2. But we did move vertically, but these are corresponding, right? These are corresponding symmetry with the x-axis. Again, it's not visually apparent because my drawings suck. But this should be negative 1/2. Because that symmetry, it's just literally flipped, like reflection over... Yeah, I should probably use that terminology. Reflection over the x-axis is what this did here. It should be negative 1/2. And that reflection just changed the vertical. So now it's negative. So this holds true for this, which is root 2 over 2, comma, negative root 2 over 2, right? Because only that vertical is changing. And same thing here. That, yeah, pi over 6. 1/2 positive, comma, negative square root of 3 over 2. Hopefully I got that right. Yeah, 1/2, comma, negative square root of 3 over 2. So our vertical, just think about the sign change. That's all that happened. Because reflection. Okay? So similar logic here. Now I probably should have kept... I'll keep one of the angles here. Just because maybe this will make more sense. So this was our, 5 pi over 6. So 5 pi over 6, this was, again, negative square root of 3 over 2, comma, 1/2, right? And the square root of 3 over 2, comma, 1/2. So exploiting the symmetry here, this will be, again, and we're going to talk about our angles in just a second. I could probably have written this a bit better just because it should be like a line here, a radius, a hypotenuse, however you want to denote it. Equivalent statements in this case. So this right here, again, sorry if my visuals are not the greatest, but just assume the stuff is symmetric, okay, when I tell you it's symmetric. That's why I'm explicitly telling you. We're going to worry about our angles very soon. Do not worry. You are okay. So here, again, exploiting our symmetry here, reflection over x-axis, And of course, in the previous cases with the first and second quadrant, it was reflection over y-axis. However you want to think of it, even function, sure. So reflection here over the x-axis, again, it changes our vertical. So we're still in the negative part of the x-axis, so negative root 3 over 2. But we're also negative of the y-axis, reflection over the x-axis, so it should be negative 1/2 this time. Same thing here. This should be negative root 2 over 2, right? Negative root 2 over 2. And then this should finally be negative 1/2, negative root 3 over 2. Okay, you're always using symmetry. Okay. So how are we going to do these angles here? So I am going to do the third quadrant angles first because we're using that logic again, initial to terminal. We're going to go counterclockwise here. So we would not be going counterclockwise if we went like this and started with the fourth quadrant. So I'm going to go to the third quadrant, kind of like, first, second, third, fourth. So doing that order, thinking of it like that is good as well. So with these angles here, I want you to first think about, again, and okay, I probably should have mentioned this, right? This was pi, right? This was pi over 2. I'm going to write in a different color here. This was 2 pi over 0. This was pi over 2. This is pi. If we do pi plus pi over 2, right, because we're going 90 degrees, this should then be 3 pi over 2. So this is 3 pi over 2. Okay, so thinking about this here, from 0 to here is 3 pi over 2 radian, or 270 degrees. So if we think about how we can get these angles, we have to use this here, this logic here. Well, actually, if we go from pi over 6 to here, hopefully you see, because this is a straight line, this is 180 degrees, right, from pi over 6 to here. Again, that's why it's so great to see the full picture, my God. So this will just be pi over 6 plus pi. And then that's just 7 pi over 6. So if we keep doing that, and again, if we, draw here, maybe this would be a good time to put back these guys right here. And again, these are not going to look that evident. Okay, that actually looks pretty straight. Very nice. Okay, so if we think about this here, our logic, again, the angles don't look, this is pi over 4. We do that plus pi. So pi over, oops, what the heck did I just do? If we do pi over 4 plus pi, okay, so that's 5 pi over 4. Right here, this angle, 5 pi over 4. Again, when I say, I should probably, never mind, because initial terminal, it's actually, the 5 pi over 4 is this angle right here. And then, of course, we're going to do this pi over 3 plus, because this is a straight line right here, this is a straight line, pi over 3 plus pi, which is the same as 180 degrees. Pi over 3 plus pi is 4 pi over 3. Same logic here. Okay, I'm just going to write the lines. I deleted them, probably shouldn't have. And again, the reason why I'm writing this, I know some things I do write, some things I don't, just to kind of, emphasize the straight line nature. Actually, no, this is bad. I should probably... All right, it doesn't matter. So if we think about this here, initial to terminal logic, this is 0 to 2 pi. This is 360 degrees, however you want to think about it. So thinking about symmetry, reflection with the it's reflection with the x-axis, symmetrical with respect to the x-axis here. These are corresponding angles, okay? Corresponding angles. This goes with this, this goes with this, this goes with this, this goes with that. This is revolution, 2 pi. In order to find this, and then this was kind of the reverse logic that we use with the second quadrant here, which is that we take the 2 pi and then we subtract that corresponding angle in that first quadrant here. So really, this would just be, this guy is just 2 pi minus, then, for example, this one is pi over 6. And then this one here would be 2 pi minus pi over 4. And then this would be 2 pi minus pi over 3. And if we actually did that here, this would be 11 pi by 6. Sorry, 11 pi by 6. And this rate, 7 pi by 4. And then this would be 5 pi by 3. So there we go. That's our unit circle. Sorry for the pauses. I was just trying to think here because, again, this is from scratch. I didn't plan this proof at all. I really apologize for the breaks in between. I was just trying to think about a good way of explaining this properly. And again, that I feel like the reason why that was just because I didn't have the full, this was a very sloppy drawing, and I wasn't able to see it clearly, the symmetry. But of course, now that I'm explicitly explaining it, hopefully you hear it in my voice, that there is symmetry in fact. Probably should have used a blank unit circle. I'll probably make a revision of this video in the future. But for now, I think it's pretty solid. I'm trying to make you guys understand it as much as possible. Of course, just due to my limitations. I mean, this is an iPad. iPad should be, maybe I'm just not using the iPad correctly. But I just find it very difficult to draw this from scratch and get the full final product. But I did prove every angle and its sine and cosine values on the unit circle, which is great. Okay, see you guys in the next one.